Welcome, everyone. Today, we are diving into efficient configuration, mastering Rust feature flags. This session serves as a technical guide to one of the most powerful tools in the Rust ecosystem. We will explore how to leverage feature flags for precise compile time configuration, discuss best practices for managing optional dependencies, and examine how to implement effective default build strategies. Whether you are looking to optimize your binary size or provide more flexible library options, this guide will provide the foundation you need to master configuration in Rust. Let's get started.
When evaluating compile time versus runtime configurations, it is essential to recognize that feature flags are more than just simple variables checked during execution. Instead, they act as instructions to the compiler to create distinct versions of a binary before it is even built. As illustrated in the diagram, a single source code base can branch into different outputs depending on the configuration. By turning a feature off at compile time, the associated code is completely excluded, leading to a smaller, more efficient binary A. Alternatively, enabling the feature results in the full-sized binary B. This approach offers three primary advantages. It minimizes binary size by entirely stripping out dead code, it enables the delivery of specific platform-targeted capabilities, and it ensures a cleaner distribution by removing dormant logic that would otherwise remain unused in the final compiled product.
To begin setting up features in a Rust project, you must explicitly declare them within the manifest file, specifically cargo.toml. By default, the features list is empty. As shown in the code snippet, features are defined under the dedicated Features section. Here, the default array is empty, signifying that no features are active unless specifically requested. We have also defined a custom feature named print42 by adding it as a key with an empty list of dependencies. This explicit declaration is a requirement before any feature can be utilized in your source code or conditional compilation blocks.
When wiring the logic for conditional compilation in Rust, we have two primary approaches, the attribute method and the macro method. The recommended approach is using the attribute method, shown on the left. By applying the CFG attribute directly to an item, the compiler completely ignores any code that does not match the active feature. This ensures the excluded code effectively does not exist in the final binary, keeping it lean and focused. Alternatively, we can use the macro method, which utilizes a CFG macro within an if statement. This behaves like a runtime Boolean check, but it is resolved during compilation. While both branches are syntactically checked to ensure the code is valid, the compiler optimizes away the unreachable path. This method is particularly useful when you want to ensure that code remains syntactically correct even when a feature is disabled, providing a different level of validation compared to the attribute method.
This slide illustrates how the build command behaves when using Rust's feature system. In the default scenario, executing cargo run follows the standard execution path, resulting in the output hello world. Here, any optional features remain disabled. Conversely, the second example demonstrates enabling a specific feature by appending the -- features flag followed by print42. By activating this feature, we trigger a modified code path that changes the output to hello 42. This highlights the flexibility of using conditional compilation to adjust program behavior at build time.
The challenge of heavy dependencies is a critical consideration in modern software architecture. As the context here suggests, you don't always need every tool in the shed. Consider a scenario where we are building a lucky number generator that depends on a large library called rand. Our objective is to ensure that if a user chooses not to use this feature, they are not burdened by the storage requirements or the compile time overhead of that library. We want to avoid bloat and ensure that our application remains efficient for every user, regardless of which features they choose to enable. Configuring optional dependencies involves two primary steps. First, mark the dependency as optional within your Dependencies section by setting optional equals true. In the example provided, the rand crate is defined with this attribute. The second step is to create a specific feature that enables this dependency using the dep syntax within the Features section. For instance, defining lucky number with the value dep rand represents the modern and explicit way to refer to optional dependencies. This ensures that the crate is only included when the corresponding feature is activated during the build process.
When implementing conditional compilation in Rust, it is essential to properly guard your imports to maintain a stable build environment. As shown in the code example, we use the CFG attribute to ensure that the RAND library is only imported when the lucky number feature is enabled. However, simply guarding the import is insufficient. You must also apply the same guard to any function or code block that utilizes those imported types or traits. Here, the print status function is also guarded. Without this secondary guard, the compiler would attempt to call missing libraries when the feature is disabled, resulting in a build error. By guarding both the import statement and the function usage, you ensure that the compiler only processes code that has all of its dependencies met. To understand the verification and impact of our implementation, let's look at these two distinct execution paths. Path A represents the default behavior. When we execute the standard cargo run command, the system ignores the RAND crate entirely. This leads to a fast compilation process and results in a standard message output. This is our baseline, demonstrating minimal overhead when specialized features are not required. In contrast, Path B shows what happens when we enable the lucky number feature flag. By running cargo run with this specific feature, the workflow changes significantly. The system must now download and compile the RAND dependency before compiling the application itself. While this adds steps to the build process, it is verified by the final lucky number output. This comparison highlights how conditional compilation allows us to keep our core build fast and lean, while still providing the flexibility to pull in heavier dependencies only when they are explicitly needed.
The batteries included philosophy is centered on the idea that software should provide everything needed for immediate use. When we look at why we prioritize default features, the first reason is convenience. Most users want a seamless, standard experience right out of the box. Secondly, defaults serve as a practical form of documentation, as they clearly define the intended usage and core patterns of the library. Finally, this approach provides a balance between ease of use and performance. While standard users can work effectively without worrying about complex configurations, power users, such as those developing for embedded systems or WebAssembly, retain the flexibility to strip away these defaults to save bytes and optimize their specific environment.
The default key in your cargo.toml file is a list of features that are enabled automatically whenever you execute cargo build or cargo run. This allows you to define a standard configuration for your project while still keeping certain functionalities optional. In this example, we have added lucky number to the default list. Under the feature section, lucky number is defined to include the RAND dependency. Because of this setup, executing a standard cargo run command will now automatically download the RAND crate and ensure the lucky number functionality is active, providing a seamless experience without requiring manual feature flags.
The opt-out strategy is a powerful way to manage your application's footprint by disabling default features. To do this, you use the No Default Features flag. As shown in the first example, running cargo run -- no default features produces a bare-bones application. This approach is highly beneficial for embedded developers who must strictly limit binary size and resource usage. For more specific configurations, you can combine this with the features flag. In the second example, cargo run -- no default features -- features GUI disables all default functionality while explicitly enabling only the GUI feature. This gives you complete control over your build, allowing you to include only the exact components your project requires without any unnecessary overhead. This command summary matrix illustrates how different flags impact feature selection when executing a cargo run command. Starting with the most basic form, simply running cargo run enables every feature defined in your project's default array. If you need to add a specific feature on top of those defaults, you use the features flag, followed by the feature name, which enables your standard set plus the one you have specified. To opt out of the default features entirely and run a bare-bones version of your application, you apply the No Default Features flag. Lastly, if you want to run your program with one specific feature while keeping everything else disabled, you combine the two flags as shown in the bottom row. This disables all defaults, but explicitly enables feature X. Real-world applications of feature flags can be seen in common ecosystems like web frameworks and serialization libraries. In the context of web frameworks, flags such as TLS or WebSockets are used to manage dependencies efficiently.
This means heavy cryptography libraries are only brought into your build if you explicitly require secure connections, preventing unnecessary bloat. Similarly, in serialization, a derive feature is often used to automatically generate code for data conversion. If your project doesn't require this automated generation, disabling the feature can significantly save on compile time and keep your development cycle fast and lean.
To conclude, let's review the key takeaways from this discussion. First, remember that crate features are used to control the availability of specific functionality within your project. Second, conditional compilation through the CFG attribute allows you to manage exactly what code is compiled based on the target environment or enabled feature flags. Finally, always prioritize designing for the user. The goal is to provide explicit, granular control for power users while ensuring that convenient defaults remain in place for everyone else.